originally from India, so if you have problems with my accent, just let me know. And feel free to ask questions and stop me at any given point. So I'm going to cover how a Linac is brought into a clinic. I'm also going to talk about how we accept it in the clinic and how we actually calibrate it. And once everything is done, what other data do we take so that at the end of it, we have commissioned the Linac for the clinic. And as far as monthly QAs go, that to some extent depends on the hospital that's going to use the clinic. So I won't go into too many details of that. Also, if you have any questions, any more details that you would like, you can email me through either Will or Credit. So let's begin. Let's say, just want to give you some introduction about what is Thanksgiving. This is one of the holidays in the United States. It was the most recent one was the day before yesterday. And what happens during Thanksgiving is, for Christmas, people buy gifts during this period. And as a result, most of the shops will give large discounts. So let's say it was Thanksgiving, and it was actually 2 days ago, and the deals were pretty good this year. So on tech, you had like 20% off. As a result, you had some money, you decided to buy a Linac. Now the hospital was very happy, we have money, let's go, we bought a Linac. They will deliver it to us within 4 to 6 weeks. Come New Year, maybe we can start treating. Well, it doesn't work that way. So a couple of reports which are produced by the American Association of Physicists in Medicine, the ABM, are used as references during commissioning of the Linac and also its acceptance. Now these reports, the TG represents task groups, and there are more than 200 task group reports specifying or recommending procedures for various kinds of therapies and uses of different machines, CT scanners, MRI, ultrasound, and so on. Our concern will be the task group report 106, which talks about commissioning, and task group report 51, which talks about how to calibrate the machine. The question I have for all of you is, do you get to see these reports? Are those reports available? Or should I send them in the form of PDF to be distributed? Hello?
Yes. You can send them. I think I've seen that for the IAEA. I don't know if they,
okay.
Yeah.
About the task group? Okay.
No.
So I will send them to you along with my slides later on.
Yeah, sure.
Yeah. Okay. Okay. So to begin with, once the Linac is here, you actually, or before you decide on ordering the Linac on Thanksgiving, you may want to sorry, what was that?
No, you can continue.
Hello?
I think it was just some. Yeah, you can continue.
Okay.
Yeah.
So you want to make sure that you actually have a bunker that is properly shielded. And I will just go over some, I'll show you some pictures to give you an idea as to how this works. This is based off the Linac that I have been monitoring, and we got it last year. So we already had a bunker in place for one of our previous Linacs, except that it wasn't for the new one appropriate, so some changes needed to be made. This is, uh, if I move the mouse, can you see the mouse moving? So,
Yes.
yeah, so this is the entrance to the bunker. You go in there, and the machine will be installed here. So this is the floor. This is the ISO center of the Linac. The Linac will be placed here, uh, will be placed at this point, and the gantry will rotate around this axis. Now, interestingly enough, this is the place where I'm talking from. So if the gantry points towards me, I want to make sure that I don't get any radiation during the day because that's where my office is located. This is the ceiling, and we are 2 floors below the ground. So we have offices on top. So we also need to make sure that the people sitting on the upper floor don't actually get the radiation if the gantry is pointing upwards while treating the patients. So how do you decide how much radiation can be allowed, or rather how much attenuation of the radiation should be done, how much shielding should be placed? This is defined by ALARA, which is as low as reasonably achievable. But even then, what is reasonable, right? If you go to this website of the NRC, the National Radiation Council, you can actually find documents describing what is the minimum, what is the maximum requirement of how low is really low. One way to do that is, of course, not to use the machine. Time. The less you use it, the less radiation anyone gets. But then that doesn't help you because why would you buy a machine? The other is if you stay at a very long distance away from it, of course, you can reduce the amount of radiation which is received by the operators as well as people who have offices in the neighborhood. That again means that you need an enormous amount of space to place all these control systems far away. Since both of these are not really practical, you have to actually put in some sort of shielding. Now, the occupational dose limit based off ALARA, which is recommended by NRC, is 1 millirengen per week. Okay, fine. 1 millirengen, what does that mean? Do we have any sense of how small or how large that is? Let's look at what happens if you have only background. Let's say you don't have a machine. I'm sitting in my office. How much radiation am I getting right now from Mother Earth? So what is the background radiation? Well, this is what the background radiation, at least in my office, is. It varies from location to location, but this you can take as kind of a thumb rule. It's 10 microrengens per hour, which per week adds up to more than what ALARA allows you to have. It's about 1.7 millirengens per week. So this is just the background that we receive anyway, moving around every single day. So the value of ALARA, which is recommended, is quite reasonable. It's almost half of what we do get. And this is occupational. If you're not in the field of radiation radiology or radiation oncology, then of course ALARA requirements aren't there. Let's look at some shielding. This, as I said, is the bunker that we have. Entrance from here, there's this wall, we call this region the maze, and this is where the Linac is located. Ideally, you would want the Linac so that the gantry rotates along this direction, so that the people In the control system, where the control center is here and the offices are here, actually, you don't need a lot of shielding in that case because radiation is coming out mostly in this direction, and this will be only scattered radiation. Unfortunately, our bunker didn't. The placement was not possible in that orientation of the Linac, which means that more shielding needed to be placed here and needed to be placed here. So these are some of the calculations. I've just put them in. You don't need to actually look at them. You can look at them when you get the notes and think about them. But you can see that the calculations, there's a report by NCRP called 151, which allows you to do these calculations. You can see this is what we targeted. Alara is 1 millirentgen per week, while we targeted 0.7316. So usually we try to keep it to about half of what Alara requirement is. Most of the times what happens is people are not there all the time in their office. So most, when they get the dose, that dose is much less. The other thing that happens these days is if you look at the diagram, this shows a completely open field. Most of our treatments, all of our treatments actually have MLCs. So the field is actually never open this much. It's only tiny small regions which are open at any given time. But the calculation does not include MLC leaves in there. So this is probably more like 0.2 or less millirentgen per week that one gets from this kind of shielding. Again, going back to the figure, as you can see, this was the additional shielding which was placed. These are the offices. Same thing here. Additional shielding for the control, for the therapists in the control room. This is the picture when the work was being done. So this is the maze. You enter from this side. The door is back there behind this. And as you come in, the machine will be installed on this side. This is that extra thing. You can see that while the shielding is to be placed, all the wiring also has to be behind the shielding. One of the issues that appear is when you have electric outlets. If you place electric outlets which are straight going through the wall from inside to outside, those electric outlets will lead to radiation leakage. So the cables are usually brought from the top, from the outside, and then come through this wall so that there are no holes because of within the field of radiation, main field of radiation, which will lead to radiation leakage. That's the shielding for the ceiling. Extra shielding was needed. Now, what happens is if you don't have enough space for the gantry to rotate, which was the case for this bunker was relatively small. Within the main, when you open the jaws and the beam is pointing towards one of the walls, in that field of view, additional shielding, as I said, needed to be placed, but there wasn't enough space to place concrete or high density concrete, so lead bricks had to be placed. Now, lead is really soft material, so these bricks, as you can see, they are wedged so as to prevent any kind of gaps that will lead to radiation leakage. And then to hold them up, there are these metal bars which actually keep them in place. If you just place them on top of each other over time, with their own weight, they will just squish down, since lead is so malleable. Once you're outside of that, then it's just high density concrete, which basically has lead balls in it, kind of ball bearing size balls in it. And sorry, any question? Okay, so it has high density concrete. Basically, is concrete with kind of lead or steel balls embedded in it, equally distributed. The high density concrete was already in place. It was the lead bricks that needed to be placed in front to enhance the shielding. Once the shielding was in place, in the meantime, for the Linac, the ISO center was laid out. Now, here's the interesting part. When the Linac, before the Linac is placed, the couch ISO center and the Linac ISO center are put in position. This is the couch mechanism. So before the Linac is placed, the couch has to be placed. The couch, once it is placed, cannot be moved. So that's one of the tricky parts with the Linac. Now, the Linac is actually heavier than the couch, but the couch is the one that moves around the ISO center, and its ISO center is fixed once it is placed, once it is put in place. So this is the couch mechanism. This is the axis around which the couch would rotate from the center. Usually, it takes about 2 months between the couch placement and the Linac to be placed. So the couch mechanism, couch is placed. You see, this was the circular region which has been covered. Now, of course, the construction has gone on and the carpet has been placed. The Linac comes in. Now, when you place the Linac, actually, the position of the Linac is then adjusted to match the ISO center of the Linac with that of the couch. It's not the other way around. The couch is placed, the ISO center is very carefully placed for the couch. The Linac is then brought in place, and this is the end where they have this hydraulic press through which they can shift it by millimeters, and the Linac is moved and adjusted so that its ISO center matches the ISO center of the couch. If the couch goes out of spec, it's a huge deal to put it back in place. It's almost impossible to do it. There's, of course, additional construction work still to be done. Some pieces of electric thing, monitors to be placed, and so on. That work is done when that work is done, actually. You want to cover the Linac. You don't want any dust to go into it, especially with MLCs, and that can be a major pain because if you have even a few specks of dust within the MLCs that come from the construction work, the MLCs will start failing very soon. Showing some parts of the inside of the Linac. This is the waveguide through which the electrons get accelerated. They come out. The target is placed in here. The electrons coming from here actually hit the target. They bend over, generating bremsstrahlung and photons. Now, all that, once you have that in place and you cover it up, fine, your Linac is in place. Yes, that looks great. Just one thing, they say, okay, we have to put the Linac in place. Let's go. And it's a $3 million question. Does it work? And it all looks beautiful. We have the bunker, we have the Linac, all electrical outlets, everything is it. Does it work? They'll say, of course it does. I mean, what do you think? Well, I have to sign this document before I can accept it. I confirm that products listed above have been tested and demonstrated to my satisfaction, and that all products listed on the attached certification have been installed and are operating in accordance with their product specifications. Well, so I say prove it. You got to prove it. As a result, this is where now I start the acceptance process. The first thing so there's a whole bunch of steps that we go through. I'll just show you some of the documentation to give you an idea of what it takes to accept a Linac. One thing was radiation versus light field. So when you go in and you say, okay, I open the jaws of the Linac to such and such an extent, and the light field says, okay, it's 10 by 10 field, but when I irradiate it, how do I know it is exactly 10 by 10? What's going on? Is my light, maybe the light field is off in terms of orientation. Maybe the radiation field is off. So in this case, you see a galvanochromic film being placed here. Then we open the jaws, say this is 10 by 10, mark it out with pen, the borders of that, then go outside and irradiate the film. If the film irradiation matches this to within plus or minus 1.5 millimeters specifications for different field sizes for a given energy. So this is 10 by 10 field size. For 6 MB energy in this case, then if it does match to within that, I accept it. If it does not, then it has to go through the process of the engineers, the variant engineers will adjust it and take a look at it and make sure. So we have 3 energies on that machine. One is 6, the other is 6 FFF, which is filter free. And then there is the imaging energy of 2.5. So each one of them, we go through this process. If it is within their tolerance specified by the manufacturer, I will go out and accept that part of it. You can see at the bottom, the customer demo is required even by variant. So the engineers cannot just walk away saying, oh, I don't really need to show this. There is a profiler. So previously it used to be films. These days now, the variant uses a profiler. So that was the field edges. The next is information about the beam. Is the beam flat and symmetric to within the requirements that the manufacturer has specified? So what does flatness and symmetry mean? Flatness is defined over 80% of the field width at a depth of 10 cm. So flatness is always, and symmetry, they're defined at a depth of 10 cm. 80%, so this is, if you look at this region as the full width, then at 80% is where we go out and calculate. So you measure the height here, you measure the height here, and check the difference. And that's where the flatness is defined. It has to be usually within 3%. And you can see, this is the sheet that you look at. Once the data is there, they analyze it through the software. Flatness requirement is 3.7. Again, this is 6. For 6 FFF, there is no flatness requirement, only symmetry requirement is there. This is symmetry has to be less than 2%. For 2.5, because it is an imaging field, it's less than 3%. You look at the field sizes, check it out, 12 by 12, 30 by 30, 10 by 10, and 30 by 30. This is, again, this region is vacant because for 6 FFF and 2.5, there is no filter in there which will flatten the beam. As you can see here, the actual flatness was 2.7, so it is within their tolerance of 3%. We sign off on it, we accept it. For the energy, they have this device which allows them assuming that the field is flat. These are wedges of, as you go along this, you can actually find from this device you can get a PDD, and based off that they will give you an energy estimate of the system. Again, tolerance here is plus or minus 2. Here it is plus or minus 1. You can see that for 2.5, these numbers that you have for PDDs at a depth of 10 are what they're quoting. Pay close attention to this number, because we will be coming back to this at when we do TG51. So this is right now 66.19. We accepted. Their spec is 67.2 plus or minus 2% in tolerance, which is where we are. Okay. When it comes to imaging, they have this phantom called the Las Vegas phantom for MB imaging. What it is it's an alloy which has different amounts. They have dents of different depths and sizes. They're all circular. You take an image of that, and based off what the depth is, you can look at the contrast, and that's what it will look at. So you take an X-ray of this using MV, and looking at low X-ray imaging or 10x or depth based on the photon energy, the question is how many holes are visible in the PV phantom. So you look at A, B, C, D, E, for example, and up to F should be visible if you're using low X-ray imaging. If you're using low X, 4 to 8, then you should be able to see A, B, C, D, E. You see that A, B, C, D, E, and you say, okay, fine. This is for low X, as an example that I'm showing you here. So this is 4 to 8 MB. Again, this is part of acceptance. All this has to go through before you sign off. In the case, now we come to the couch also has tolerances. This couch actually has a roll, and it can tilt up and down, which is the pitch. And then, of course, it has the XYZ axis along which it can move forwards, backwards, to the left, up and down, left and right. And we had an interesting situation here. The situation was that when they brought this couch in and they said, okay, we have our test, we'll run our test, and you can see what the position of pitch and roll should be here. The position is in degrees. Pitch, 0 degrees, plus or minus 0.25 degrees is their tolerance. Well, this was fine. We went on and started looking at it, and when it came to roll, actually, they started going out of spec. This was the digital level that they were using, so we said we don't accept it. Okay. We tried it twice. Finally, they said there's something wrong with the couch. They had to bring in a new couch, replace it. Now, this is not the ISO center of the couch. This is just the top part of the couch which is being placed. So it delayed the whole process by about 10 days. Then they put in a new couch, and finally, after working on that, as you can see, I accepted it after the third attempt, first, second, and this was the third attempt. In between, there were other attempts that we didn't even record. So the process of acceptance can get quite tricky if things are not working as they are expected to be working. It's stressful for the engineers, it's stressful for us, but most importantly, do not give in when they say, yeah, well, you know, it's 0.5 mm or plus or minus 0.25, it's just a little beyond that. Do you actually even use the couch for that purpose? That's one of the arguments that they will try to make with couch or something else. also just say, nope, this is your spec. It has to be met. Otherwise, we don't accept your machine. It may delay the process, but at least you know that you will get a system which is in proper condition to begin with. Then you go out, you check the interlocks, everything else, and you're done. So now we have accepted the machine. The next stop is to actually start taking data. This is the exciting part. At least that's what I feel. The water tank, it's there finally. We have placed it in position, and we have the machine all ready to go. So the first thing that you do is you actually do an initial calibration of the Linac output. What that means is when these Linacs, they actually are pulsed. It's not like a continuous beam, as many of you are aware. It gives out photons in pulses. Now, as that is happening, how much does, it's not exactly a pulse, but I'll use the word because it's more intuitive. How much does each pulse correspond to in terms of dose, which is being given to water and equivalently to tissue when the patient is in position? For that, we use these task group 51 recommendations on clinical reference dosimetry. But the point is that initially, when you are calibrating the Linac output, it doesn't have to be perfect, because there's a lot of data that is relative data that you're going to take. And all you want to know is you're within a couple of percent of whatever calibration you're going to finally have the machine for when it is to be used for patient therapy. So at this point, we do the initial calibration of the Linac output using TG51, but we are not too worried about it because we're going to do it a couple of more times later on. The data that we're going to take based off that is going to be relative dosimetry, so it won't change just because of the output. Now, one of the choices that you have to make is what detectors are you going to use? Ion chambers and diodes are two of the options since you're going to put them in water. We had various detectors. We had A4, I think this was, A4's, this is the micro diamond detector. This is a newer detector called so this is a diode which we have been using previously. This was, forget the name of it. It's a special diode which came out. We didn't find it really. The name will come to me. Very useful. The micro diamond detector, actually, that's the one we found out to be very stable. The ion chambers, of course, you have to use for your dosimetry. Now, the choice of the diodes depends on the collection volume. The smaller the volume, the better it is for us, especially with ion chambers. I think these have 0.001 cc's as the collection volumes. So which one should I use? We actually went through a week of testing which ones were the most stable and provided us with the best results. For small fields, that is fields less than 3 cm by 3 cm, you have to use diodes. Ion chambers actually don't work at all. So what kind of data do we take? Well, we have the central axis PDD, of course. Then you have output factors. If you're using blocking trays, then you need the tray factors. Multi-leaf collimators, you want to check the characteristics of that. Central axis waste transmission factors, dynamic wedge data, transverse beam profiles, off-axis energy changes, whatever they might be, uh, entrance dose, and interface dosimetry data. All this is listed and uh, in proper form in the task group 106 that you can refer to for more details. I'll send that as well. Now, how do you know a detector is good? Right? I kept saying, oh, you have to choose, you have to compare. Well, here's how you go about it. The gold standard is the calculation. This is the AAA calculation, which provides you with data for different X and Y. X and Y are the field sizes along X direction and Y direction. 10 by 10 field, 3 by 3, 5 by 5, so on. You have the output factors that you measure for that. You have AAA values, and you ask what is the difference in the two, the measured versus the calculated. This AAA model is actually easier to calculate, but has to be verified as well. That's part of the planning system. It has been verified and cross-checked previously based off Monte Carlo calculations. Now, for a particular detector, this seems to exceed, the difference is more than 1%, and so it shows up in red in our Excel sheet as a clear indication, while for another detector, it's within the range of what we would expect. As a result, you would choose your detector based on your comparison with calculation. Some reference data is obtained or given by the vendors. They don't necessarily give it out for true beams. For TX machines, they used to. They call it the golden beam data. That's another way of checking, doing a cross-check of what your outputs are and whether a good reason for doing it and not just accepting what the vendor has given to you is that tomorrow when you do your annual, so you want to check your machine, it's always good to have your own reference data. If you don't have your own reference data, then you don't know if the machine has changed over time. You may keep looking at the golden beam data, but it's hard to say if there's a particular change that happened after maybe some repair was done. So before you start reading, you have, at least at our place, we have 4 to 6 weeks. We take extensive amount of data so that we know that tomorrow, if the machine goes down, major repairs are done, we have some reference that we took before the machine went down that we can compare to and make sure that we are back to where we started. I'm showing just PDDs. You can see the PDDs for different. So this is for 6 MV energy. We go down to about 30 cm. And these are the field sizes, various field sizes. And it takes a lot of time to collect all this data, but it has to be done. When you do profiles, same thing. You can see the profiles at different depths, 1.6 cm, 5 cm, up down to 30 cm. You can see the spread as the beam is spreading out as it's going down into the water. You can see these so you can see the AAA values here, and you can see the data that we took. This is cross plane, that's why it says XP. This is for 6 FFF beam. As I said, flatness is not looked at because there is no flattening filter, so you can see the profile. It is angled, it is curved. Once you have this data, now you can go back and start doing TG51 to bring the machine into condition. Usually between the first TG51 and this one, at least for us, it takes about 3 to 4 weeks. There's a gap while we are collecting the rest of the data. So TG51, clinical reference dosimetry, one of the most important things that you need to do for calibrating your Linac. What is clinical reference dosimetry? So this is what TG51 describes as clinical reference dosimetry. It is the determination of absorbed dose to water per MU under reference conditions in the clinic. Do you know what MU is? MU stands monitor unit.
Monitor unit.
Sorry?
Yeah.
Okay. So MU stands for monitor unit. Think of it as a pulse. It's a bunch of pulses, but let's think about those as bunch of pulses put into a single unit, kind of. So of photons coming out of the Linac. So dose to water per monitor unit. Now monitor unit is something that actually the machine shows you when you are giving dose. That's what the machine has. There is no relation between monitor unit with dose until you adjust the amount of photons, the number of photons coming out per monitor unit. So dose has nothing to do with monitor units until the physicist tweaks the machine in such a way that there is some sort of correlation between the dose in centigrade or gray and has a one-to-one correspondence of that with the monitor units. So that's essentially what clinical dosimetry is, or reference dosimetry. That's what we are going to set up using TG51. We are going to tell the machine, look, only when you have this particular monitor unit will this correspond to this particular amount of dose being given. Okay, so to do that, let's say you start with an ion chamber. We always start with an ion chamber for that. This is a curious curve. What I'm showing you here is if you start with an ion chamber, this is an A12 ion chamber curve. Ignore the red lines. That's something that I have drawn. But the manufacturer will give you this of the ion chamber. The manufacturer of the ion chamber will give you this plot. What does it say? Let's look at it. This is cobalt 60. So it's about 1.17 to 1.2 MV or MeV. Okay? With respect to this number, so what does this say? This is how much charge would be collected by the ion chamber if you put it in a cobalt beam. Now, why is it 1? Because it's not an absolute charge. What we are looking at is if you put it in different beams, so this may be, it's about 140. These dots that you see here, they correspond to different energies, usually from radioactive materials. And as the charge gets collected for different energies, the charge kind of keeps increasing. What you see there is the ratio of how much charge is collected for each energy as compared to cobalt. So you take the charge for one energy divided by the charge by cobalt, or vice versa. With cobalt, charge with respect to itself is 1, and then as the energy goes down, that ratio decreases and then goes up. So this is essentially an energy response curve of the ion chamber that you would get from the manufacturer. Now, the problem is it stops at cobalt. Your machine is, let's say, you're looking at energy 6 MV. Well, there's no curve there to begin with. I have drawn tangents here to the lowest value that it goes, and that turns out to be about 0.95. So this is 5% lower. And symmetrically, if you go, it's about 5% higher. So those are the two lines that I've drawn. Let's say this curve keeps going up. Looking at this, if you did not do anything to your ion chamber, chances are you will be off by 5%. Now, how would you know how good or bad your ion chamber is when you buy it? Well, you don't know. For that, what is done is you take the ion chamber and you send it off to a lab which will calibrate it for you. The calibration, and in this equation where you're going, this is the dose, this is the charge which is collected by your ion chamber. This quantity is the calibration value that the lab will send you when you send the ion chamber to them. Now, this number that you have here is for cobalt. In our ion chamber, for example, this is the number that we got for one of our ion chambers. What this number gives you is actually the amount of charge that you will gather. How much does that charge correspond to the dose? So you get that right away. What this means is per coulomb, it is 10 to the power 7 grays of dose will be delivered. That number is given to you by the lab. Now, what's so special about this lab? At least in the United States, this lab has to be approved by the National Institute for Science and Technology. So the lab, the number is provided to you by a lab that can be traced back to the NIST, giving them the approval to calibrate an ion chamber. So that's why it is NIST traceable lab. So you have your ion chamber, you send it out, it came back with a calibration curve, with a calibration number for cobalt. But you know, looking at this curve, that the ion chamber is energy dependent. As a result, you need to be able to actually go ahead and make some sort of correction to allow for 6 MeV energy. That part, an additional calibration factor, correction factor, is what this KQ is. So this quantity here, that quantity actually comes to you from the NIST traceable lab. But KQ is something that you have to measure for your machine. It's called the quality conversion factor. It accounts for change in absorbed dose to water calibration factor between. So if you read that on your own, it's going to be extremely confusing. The bottom line is KQ is obtained from our measurement, and the question is, how do we do the measurement? Okay? This is how we proceed now. What we have is, to obtain KQ, we have to have the source, which means we have to have the water tank placed such that the surface of the water is at a distance of 100 cm from the source in the Linac. This is called the source to surface distance of 100 cm. TG51 says that it is essential to use it. You have no option. We have no options. Okay, if you're going to follow TG51. As a result, the SAD setup is not to be used for this particular measurement. Now, let's say we went ahead, we did this measurement, we got a KQ factor, and I will come back to this in more detail. Then we come back and ask, okay, we have KQ, we have this, N, we are left with M. This is actually the charge that will be measured by the ion chamber when you have put it in the radiation field. So how do we measure the charge? Well, the electrometer that you have connected to the ion chamber is going to give you some value for charge. Let's call it M, a raw value. It needs to be corrected for various things. The full equation is the following. You have ion chamber correction, ionization, inefficiency correction. This is temperature and pressure. This is for the electrometer. This is the polarity issues that might arise during measurements. You take all that, all those corrections, multiply M raw, and you have the final value of M. So polarity correction, what that says is, look, on the ion chamber, you have a positive and a negative applied to the two electrodes. And when ionization happens, the two collections, the positive and the negative ions get collected on different electrodes. Well, is this going to be, does your system actually care about it? So you take a value by having one electrode giving positive voltage, the other one negative, do a measurement, that's M raw plus, then flip the polarity, do a M raw minus, take the difference and divide by the mean of the two. That's the polarity correction that you have to apply. The electrometer correction, it's basically a calibration factor. So you send your electrometer out from the NIST traceable lamp. Again, you will get a factor. Usually it is 1 or very close to 1. The pressure and temperature that you have within the bunker where you're doing the measurements is what you apply. Now, there is no humidity correction, but TG51 actually is valid between a humidity range of relative humidity range of 20% to 80%. If it is extremely dry or extremely humid, suggestion is don't do TG51, wait for another day, or in some way or the other fix the humidity in the room. So pressure and temperature corrections, these are basically based on gas laws that we have all learned in basic physics courses, and you can actually derive them on your own. Ion chamber collection inefficiency. So ion chamber, if it is not collecting, so The first one, the polarity correction, is you're just switching the polarities. In this particular case, you are changing the voltage. So you would take one measurement at, say, 300 volts, and the next one, we usually do it at 150 volts. We have the voltage, which is VL, the low voltage. VH is the high voltage. Take the different voltages, do the measurements for the charge, M raw H and M raw L, corresponding to high and low voltages, and then apply this. Again, this has to be very close to 1. If it is more than 5%, don't use your ion chamber. There's something wrong either with the ion chamber or the electrometer. These details are provided in the document which I'll be sending you. I just wanted to give you an overview because the document itself is kind of long and obtuse, but this is essentially the process that that is followed for TG51, and this is for photons. Now, when you are doing the charge measurement, you don't have to use SSD at 100 cm, and the ion chamber need not be is to be placed at actual depth, not effective depth. I have not spoken about the difference between actual depth and effective depth. What that means is when you have a cylindrical ion chamber in a beam, the place where the maximum or the effective ionization seems to happen is not at the center of, is not along the central axis. It's slightly above that. And that's what it means by effective depth, that you have to subtract that small change. It's described again in TG51. A good reference to actually understand that is Khan's book on radiation therapy. Okay, now, so all the factors are now in place. To determine the dose based off the charge, we have KQ. This came from NIST, the value for M. KQ we did determine. M we determined by applying all the corrections to it. And so finally, we have a value for dose, which means that what we know is for that given charge, how much does that charge correspond to in terms of dose in units of gray. Well, having done this, now I will proceed to show you how things are done at our place. And I will have examples for you. So at your institute, if you're doing things, so you're going to get a Linac, you should be able to get started. So clinical reference dosimetry at BWH. Photons. Both these equations, we have been through it, you know what they mean. Okay. What we do is we put that tank, we set up SAD setup for the measurement of M. Remember, for the measurement of KQ, it has to be SSD, so there's nothing to be changed. For M measurements, there's no specified SSD. We use the SAD setup, which is shown here. So 90 SSD, ion chamber is at a distance of 100 from the source, but it is now at a depth of 10 cm. So it is the source to axis distance. That's what SAD means. SAD setup for M, for the value of charge. Depth, 10 cm, as I just mentioned. Linac is calibrated at Dmax. What does that mean? That means that at the depth where you get maximum dose, one monitor unit will correspond to 1 centigrade within 1%. And we'll come back to that again. But 1 monitor unit will correspond to 1 centigrade. That's at a depth of, for 6 MV, it's 1.5 cm, because that's where the maximum dose from 6 MV is delivered. Clinical TMR curves are used. Again, I'll come to that on the next slide. Any questions so far? I mean, there's a lot of stuff that I'm talking about.
Yeah.
Yeah.
Hello, Dotun?
Yeah. Yeah.
Sorry. No, I'm trying to hear if Dotun is speaking.
Oh, I see.
Okay.
No, Dr. is there, but I'm not the one speaking.
All right, no problem.
Okay. Any questions? I mean, there's so much that I've been talking about, so I don't know.
Yeah. Okay. So I have some questions here from.
Yeah.
Okay, I have some questions here from Omojola.
Okay.
He says, I think you answered one of. Okay. So what recommendation would be adequate and most simplified for calculating transmission factor of a Linac room?
Sorry, what was that?
So what recommendation would be adequate?
Oh, I see. So the recommendation is actually given in a document by NCRP 151. In terms of how you calculate and what you need to consider, comes down to ALARA, what I had shown before, that it has to be less than 1 millirangen per week. And if you use low density concrete in your calculations, you will see that for 6 MV, to get attenuation less than that or transmission less than that value, it can be as high as about 10 feet of concrete. If you use lead blocks, it's much less. Now, is that what the question was?
Yes, I guess that's what it meant.
Okay, and then here's another thing which I did not mention here, because I was looking more towards 6 MV and we have limited amount of time. But let me just mention in passing that if you go to 10 MV and more energies, then when you put lead, there's a lot of neutrons that come out, and those neutrons then have to be stopped as well. So for 10 MV and higher energies, it really becomes quite difficult to use lead, and then you do need concrete which has hydrogen in it because of water content, and which stops the secondary neutrons more so. So you could put lead over a certain part and then have concrete after that to stop the neutrons. So to reduce neutron contamination. There's also polyethylene that is used for that purpose.
Thank you. There's another question. It says, is Monte Carlo simulation ideal for barrier thickness calculation of the type of Linac facility? Okay, if the type of Linac facility is known.
Yeah. Monte Carlo is the gold standard. So yes, if you can commission it properly, absolutely, you can use it. The only thing that happens with Monte Carlo is to get the required statistical accuracy that you want, you really need to run the Monte Carlo simulation for a very long time, or you need really powerful computers. For shielding calculations, as a result, it's easier to or it's faster to do an estimate based on analytical formulas. But if you can commission a Monte Carlo and you have the required computer capacity to run it, of course, it's the best.
So how do you develop the skills to use the code, the Monte Carlo? Because most physicists back in Nigeria can't use it as well. Back in Africa.
Yeah, right. Well, what I showed you there, as far as the shielding calculations were concerned, we don't use Monte Carlo for our shielding calculations. And as far as I know, not many people do it because it's great on paper to use it, but in practical terms, it's extremely difficult because of the amount of time that it takes and the amount of investment that you have to make into it. Most people will take a small problem, for example, say you don't know how many neutrons are coming through a certain region because you did a measurement with your device and you said there are more neutrons coming through. Then you will use a Monte Carlo to investigate that, but that will turn out to be a 6-month project, which is only done out of curiosity and not for practical reasons. So I know in Africa, in most places, even here, we don't use Monte Carlo for that purpose because it's just too time consuming and it requires too many computational facilities. Problems with Monte Carlo usually are more like research based rather than clinical problems that you try to address. Yeah. Now, if you do want to use Monte Carlo and you do have the facilities to investigate small problems, which can be done on a desktop, there are codes available free that you can download that many people know. There's the Giant 4 from CERN that people have adjusted for medical physics specifically. There is the EGS NRC code from Canada that you can go online and download for free. Both these codes are free. And EGS NRC is, I think, much more easier to use than Giant 4, but both of those are free and can be used for medical physics. Anyone wants more details, I can send them to you. So.
Thanks.
Yeah.
Are there hard and fast rules in the design of treatment room?
Can you repeat that? Sorry, I didn't get that.
Yeah, this is someone's question. I think it's been answered. Yeah. It says from Omojola, are there hard and fast rules in the design of a treatment room? I think architectural design or something.
So, is there a fast rule?
Yes.
No, it's basically a LARA. I mean, see, the thing is, you can put, instead of, say, 10 feet of concrete, you can put 15 feet of concrete, and that's great. If your calculations show 10 feet of concrete is enough, and you want to spend more money putting in 15 feet of concrete, that's fine. No one is going to stop you. It will be great, except the people are going to pay for it because now you are adding 5 feet of concrete for no reason, right? The rule comes down to LARA. Look, do not let people who are working get more than 1 millirentgen per week of radiation dose. As long as you can keep that in, that's fine. An extreme idea would be, if you have the space, let's say you're in the middle of a desert, right?
Yeah.
Or you have a lot of space. You can put a Linac and operate it half a mile away from it without putting any shielding at all. You can put it in a very tiny and a nice building with no shielding, as long as people who are going to operate it and offices are away from it, say half a mile away, then you don't need any shielding, right?
Yeah.
That's the basic idea that, okay, shielding is determined by only one number. It's alarm, as low as reasonably achievable. As long as you can put it to less than 1 milliradian per week, you're good. You can use whatever materials you want. You can not use anything, just be far away from it. Put it on a truck, take the patient, and move the truck a mile away from everywhere and operate it. As long as the operators are remote, doesn't matter. Yeah, I mean, that's what it is. That's why I put in the time and the distance. The distance is actually key. If you're far away, you don't need to put in any shields.
More questions?
Yeah.
Sorry, I have still. Can we make shielding calculation based on technique to be used? Like if the facility is dedicated to only VMATs, we may
No,
reduce the thickness.
no. So what VMAT, yes, you do. If you're using VMAT, you can actually include that. There are thumb rules which are specified in that report. When you have MLCs, what you should use, what numbers, how much you can bring it down. It doesn't have to be an open beam calculation. So yes, you can reduce the amount of shielding that you have. You can also have systems where, so the bunker that we were in, right, the one that I was showing you,
Yes.
this had a really old Linac, okay? And
Yes.
this was only used for total body irradiation for pediatric patients or grown-ups or adults. And the way it was that this was a home-built Linac that we had, which gave out 4 MB energy, and about 40 years old. We had a hard time maintaining it because the parts are not available anymore, many of those. But the way it was done, because it was TBI, there was a source from the top in the ceiling, and there was another source in the floor of the ceiling. And there was no gantry that would rotate. And the patient would lie on a bed, on a couch, halfway between the two sources. And because it was total body, the field was open. So the only shielding which was required was on the top. Our side shieldings were really low. And that's why I showed you we had to enhance those shieldings when we put in a rotating gantry Linac. So yes, specific to the Linac and specific to what you're going to use, you can change your shielding. Again, it comes down to same thing, Alara. You can go outside and you say, okay, I have built it. Now, you may have to enhance some regions where there may be more leakage, or you can reduce the shielding and say the fields are going to be really small, so I don't really care about this open field calculation. On the conservative side, at the Brigham, we always do it with the open field so as not to have any trouble at any point. Let's say tomorrow for some reason, your system fails and you just have a completely open field for 5 minutes. There's going to be issues that are going to be raised by the state, by the NRC. It's just more conservative to shield for open field and say, we are good. It doesn't matter how you do it. Let's say you're using the machine for research tomorrow, and you want to do open field measurements. If you shield it for VMAT only, you may not be able to have the beam directed in a certain position. because you didn't shield it for that open beam. So from the conservative point of view, it's always good to have an open beam shielding rather than just for VMAT.
Okay.
But you can do it.
Thank you.
Yeah.
Yeah. So I think so this one asks who designs the layout of the Linac bunker? Is it an architect or a physicist?
Right. Great question. So at least at our place, we do have an expert. So our previous chief, Lee Chin, he actually started doing these calculations about 15, 20 years ago. And he's the one who has now trained a couple of people who were interested to do the calculations. But it is not the architect. Usually the architect company is not, they don't have people who can do these calculations. If you don't have an in-home person, then you usually would be looking to hire someone separately outside of the construction company that's going to construct the bunker to do these calculations. One of the things that you have to be careful when you're doing those calculations, that after you do the calculations, the people who are going to construct it, keep a close eye on them. We had a situation where they forgot to put in some bricks, lead bricks, and then after the bunker was built, the Linac was put in. When we started doing radiation surveys, we saw certain regions where we were getting radiation 10 times what it was supposed to be. So we had to go in and fix it. And the person in charge was fired by the construction company.
Okay. All right. Thank you very much. Any more questions?
Yeah.
All right.
So
Okay.
I have maybe like four slides to finish if you don't have questions.
Okay.
Okay.
No more questions. Yeah.
Right. So let me just remind you where we were. We have this. I was explaining how things are done at the Brigham. We use clinical TA markers, and the reason for that is this particular paragraph from TG51, the document, as I said, I will send it here. So if you have absorbed dose at other depths in the clinical photon beams, they suggest how to go about it and what to use to calibrate your machine. The highlighted part is the one that we use. We calibrate the machine at Dmax. That is why in such situations, the clinical tissue maximum ratio, the TA markers, is what we use to calibrate it. I'm going to send you this as part of the notes.
Yeah.
If you look at this part, that describes the full procedure of the measurement. Set up the tank, apply bias, take ionization curve using the tank, apply upstream shift. So upstream shift for our chambers is 0.6 times the cavity value. So if the cavity value changes based on ion chamber, you will have to choose your own. Notice what we got at depth of 10. We got 66.1. And if you recall, I had asked you to remember what the vendors had given, 67.1. So because that was the way they used their method of measuring it, then you go on and reposition the tank so that SSD is 90, and then move the ion chamber to 10 cm. This is D actual. So SSD is 90 cm. And then At the bottom, actually, I have a result which doesn't show up. I don't know this. Anyway, which you should be able to see. So this is for photons. Our final result is the following. After we are done with that and we do the measurements, per mu, it's 1 centigrade, and this is 0.68% off, which is acceptable. So 1 centigrade corresponds to 1 mu. This is the TMR value which we have from our measurement, and you can do the same. So what I have given you on this slide are all the details of how a procedure can be developed. Notice the calibration factor is included here. This was done last month by 3 of us. It's usually good to have a second pair of eyes to check everything, even though one might have done this a few times. Okay, so that completes TG51. Now your machine is almost ready to use. What you need are daily and monthly checks. What we have started using is the sun nuclear device called the daily checker. You calibrate it and set it up for a daily check, and we have a monthly phantom as well that we use. All this, once you are done with it, you still need, or it's good to have, a second independent check on your calibration. And for that, we seek the help from the Radiological Physics Center, RPC, in Houston. They will send us the OSLDs, give us a set of OSLDs, the phantom, all this entire system. We provide them the irradiated OSLDs from our machine. The procedure is also described by them. And then within 2 weeks, we will get the result from them. To within 1%, we are very happy. If it is not within 1%, then we have to go back to the machine and ask. We have to adjust our machine accordingly. Once this independent check is done, then we start actually planning patients for different machines or for that machine. And then start training the therapist to follow a QA workflow. We have developed the QA patients in the system, checking beam configuration, put the stuff in the treatment planning system, cross-reference dosimetry in similar machines. So this part, cross-reference dosimetry, is only because we have multiple machines, and we try to keep at least 2 machines that are matched with each other so that if one goes down, the patient can be treated on the other machine. If you have a single machine, of course, there's no cross-reference dosimetry for similar machines. And then we do a IMRT QA for some of the patients that are done before they get treated, and that provides a good final check. At this stage, you're ready to go out and treat the patients. Thank you.
Okay. Thank you very much, sir. Yeah. So
you're welcome.
Yeah. Any more questions? All right.
Yeah. Good evening, sir.
Okay. Sure.
Thank you very much for the presentation. Yeah.
Okay.
I would like to, when comparing TG51.
Network. Hello?
I can't hear you.
We can hear you. Can you?
Can you hear me now?
Yes, we can hear you now. Yeah.
Okay, comparing TG51 with TRS-398.
Okay.
What can you say about the comparison of both of them? Then also, let's say peradventure, you have 2 chambers. The first one, you know the calibration factor for it, and the others, you don't. is there anything, is there any process that can be done to extract the calibration factor of the unknown using the calibration factor of the chamber, without necessarily going to the SSDL, even though I know that that is the protocol, like something to improvise. That's all.
So let me understand your question first before I answer it. Can we, are you saying, is it possible to use different SSD for calibration? So one thing I can tell you, I don't know exactly what the 398 protocol of the IEA is or ESTRO is. So I can't comment on that. I can comment on TG51, any changes that you might want to make. And with respect to that, what was your question?
Okay. In my center, we use 398 for absolute dosimetry. So,
Okay.
and so I've known about TG51 before, but I've never really worked with it. And I felt this could be an opportunity to have an insight into how.
Yeah, it's breaking up, your voice.
Yeah, we're not really getting the question, but you can type it and then Dr. Mandar will say it. Just type it in case you hear me.
Okay.
Yeah, I am.
Yeah.
Just type it. Yeah. So someone also typed a question: at what interval of years does those check
Right.
those check require calibration? Okay.
So it is, at least within the US, it's annual.
Yeah.
We check the outputs monthly and adjust the machine, but the TG51 we perform if there is any major change. If there is any major change or anything that your system, that your machine goes down, and any new, for example, if you're replacing the target or making some change where you don't feel comfortable treating the patient based on monthlies, then you would go out and do definitely do the TG51. Otherwise, it's always on an annual basis that we do the TG51.
Okay. All right. Thank you very much.
So I have calculating of a Linac. Okay, so looking at some of these questions that are typed, I guess I have answered some of
Yes,
them.
you've answered all of them actually. So
Okay.
Maruf just sent his question now and is comparing TJ51 and TRS T98. Which one is better?
Right. So can he hear us? Because it
Yes.
would be easier to answer verbally. Okay.
Yes, you can hear us.
So there are two ways to look at it. One is better in terms of actually which gives better results, and I think there is no difference along those lines. Both of them give the same result. They are equally. Now, which one is more convenient, as in terms of which one is better, that I think is dependent on the user. I don't know exactly what TRS 398 wants you to do, but there used to be a TG 21 previously, and the TG 21 actually was based off using stopping powers, and it was an extremely complicated process to do it. So TG51 turns out to be very much more convenient to use than TG21. If TRS 398 is based off stopping powers, maybe it might be more tedious, but if you're used to it, maybe you find it more comfortable to use. That's what I think.
Yeah. Thank you very much.
Yeah, there was something I want to ask if there is a possibility that treating heavy patients can affect the couch. What's heavy? We have patients being treated up to 350 to 400 pounds, and no, it doesn't really affect the mechanisms. But you need to know what is the tolerance for the couch, what is the maximum weight that the couch can take. Recently, we had a brachy case where the patient was almost 400 pounds, and we could not use our CT scanner because the couch was not, could only hold 350 pounds. So we didn't want to risk putting the patient there. As long as the heavy patient is within the tolerance of, within the maximum weight that the couch can handle, you should be fine.
Great.
I think the last question, how best can we get the chamber factor of an ion chamber in the absence of SSDL? Yes. Well, you can. The problem is you need a cobalt beam. That's the most stable beam. So it won't depend on your, which makes it tricky because now you need two machines. I would say maybe you can develop a protocol for that. Or if you want, we can think about it. I think it's Maruf Adewole
Yes.
who asked that question. So, so what's your background, Maruf?
Well, I'm a physicist at National Hospital Abuja, and we have some chambers that's where the chamber correction factor known, and there are some other chambers that has been calibrated for load. And when we use it in our reading, the readings it gives us, it's too high, and we felt maybe the chamber correction factor is out of place and something like that. So what I want to do is, for those chambers that we know the correction factor, if we give them 100 MU, of course, the 100 MU for chamber 1 is also the same thing as 100 MU for chamber 2. Is there any formula that governs the relationship between both of them that we can do some relative comparison and from there extract the chamber correction factor of the chamber that we are not sure of its factor?
Yeah. So how about this? Credit, can you give Maruf my email and then we can talk?
Oh, sure.
We can think about it. This is a question which I've wondered about because I come from India and I think, well, if there's no ADCL now, what can one do in India, right?
Yes.
So it would be an interesting question to address. Is there another way that we can actually, within maybe like 3%, be able to find a factor?
Yes. Yeah,
so Maruf, maybe we can chat about it offline later on. If you email me, and then we can go ahead and look at it. Yeah.
Yeah, great. Thank you. So Maruf, please, you can just send me an email immediately after the class, and I'll copy both of you so that you continue the conversation. Yeah. Because I don't have your personal. I'm sure I have your personal email, but I won't know if it's you because I have to go through the websites to look for it.
Yeah. I'll send you an email.
Yeah. Thank you very much. Yeah, great.
Prior to Linac installation, as you mentioned, please comment more on its determination. So.
Yeah.
So this, we usually don't determine it. This is done by the manufacturer. So Varian comes in and puts that in. And then once the Linac is installed, that's the only time you can determine that because you need to be able to have either some sort of light field or radiation field to determine the ISO center of the couch. So there are tests once the Linac is in place, but before the Linac is in place, it's as physicists, we actually don't determine the couch ISO center. It has to be, you can work with the manufacturer and make sure that it looks fine, but the ISO center is defined with respect to the Linac as well. So without the Linac, it doesn't even mean much to have the couch ISO center. It's a rotational axis that you would say, okay, it's fine or not.
Okay.
Yeah.
Thank you.
Okay.
Yeah. All right. With this, we come to the end of the class. Thank you very much,
Yeah.
Professor Mandar.
Yeah. Thank you.
Yeah.
This
Any
was
further
fun.
questions?
Enjoyed
Yeah.
it. I hope you did too.
All
I
right.
hope
Thank
not
you.
too many people fell asleep.
No. Thank you very much.
You're welcome. Okay. Thank you.